Hello, my name is Isaac from First Tech Challenge Team 701, and I will be talking about scoring strategy and identifying subsystems for this upcoming First Tech Challenge season. So, the basics about First Tech Challenge. So, First Tech Challenge is a global robotics organization which is focused on introducing middle school and high school students to STEM through engaging robotics challenges. Each September, this organization called FIRST releases a new robotics game. And based on this new game, teams around the world will engineer a robot and document their process in preparation for competitions. First Tech Challenge games pit two alliances with two robots each against each other, with the winning alliance being decided by the one that scores the most possible points. Games are 2 minutes and 30 seconds long, and they have different periods that split up this time. All about autonomous and driver-controlled periods. So the autonomous period is the first period of a First Tech Challenge game. It is where the robot is controlled by pre-programmed instructions. Various tasks can be completed by your robot in this period, and tasks completed in this period tend to award more points. Human players are people that can interact with game elements and introduce opportunities for robots to score within the autonomous period as well. So the next period after autonomous is the driver controlled period. This is when your robot is controlled by human input, usually through a controller. You can have one or two drivers from each team use controllers to drive the robot and score points manually. There's going to be an 8-second transition period between autonomous and driver controlled period, so the drivers can pick up their controllers and get ready to drive the robot. Points in this period can usually be scored much faster than the autonomous period. However, they are usually valued less because they're much easier to score. And then the last 30 seconds of a First Tech Challenge game is known as Endgame. In Endgame, special twists are introduced to the game that can only be completed within this time. So for example, making your robot hang, or having two robots park within an 18 by 18 cube, that would be seen as a twist. And these twists reward a lot of points if they're completed. So if possible, and you can complete the endgame twists, that may be a good idea. All about scoring. So every FTC game will have nuances to scoring that are necessary to identify and utilize to score the maximum possible points. For example, in the Into the Deep game, you could either score samples or specimens. So to design a very successful robot, you kind of had to pick one of these two ways of scoring and stick with it. So, for example, you can have a robot that could only score the samples, which was much faster, and these robots tended to score the samples very fast. Or you could have a robot that could only score the specimens, which took a little bit more time, but awarded more points than samples. So making that decision and catering your design to that decision gave teams the most success. And as you can see here, here's a robot that was optimized to scoring samples. So those are those little yellow blocks right there. So this robot cycled very, very fast and was optimized just for scoring the samples. So some FTC games will have a strategic way of scoring that you need to optimize during the game strategically. So for example, the center stage game, which was 2 years ago, had mosaics, which introduced a cool strategic twist to the game. So human players from each team had to coordinate with their drivers and make decisions on the fly to make their teams score the most mosaics. So they could introduce the game elements and introduce opportunities for the teams to score, but they also had to think about what colors could make the most mosaics possible. As you can see here, the mosaics are the 3 colored ones put together. Also, coordinating with other teams was a very big part in the strategy in this game, and you really had to be actively talking to your teammates in a game to be the most successful. All about subsystems. So a subsystem is an individual part of a robot made to complete its own specific task. Subsystems are what make up your robot. So individually, they're made to complete their own task, but when all put together, they can create the function that the robot is meant to complete. So in First Tech Challenge, there are usually 4 main subsystems every robot has. So one is a drivetrain. As you can see here, you have your wheels. This is a parallel plate chassis. So you have plates and they hold the wheels together. And then behind that, you're going to have motors. So that'll make your robot drive. You also have intakes. So intakes can either be active or non-active. I'm going to talk about that later. But basically, those just take in the game elements. You also, some games have extensions. This game doesn't because there's a limit set on that, but extensions allow you to extend parts of your robot out to reach game elements that are far away or behind like a certain wall. And then finally, you have outtakes and deposit mechanisms. So this can be seen in the form of a claw, a shooting mechanism for this game, stuff like that. So here are examples of some intakes. Up here in the top right, you can see there is an active intake. This is any intake that can pick up game elements without driver input. So this will freely spin on its own, and it will suck in game elements fairly easily without the driver having to put in much input. And then in the bottom right here, you can see there's a claw. Claw is just any intake that uses 2 arms to squeeze and pick up game elements. So for drivetrains, you have 2 main examples, kit-built drivetrains and custom drivetrains. The main difference between these is customization opportunities. So like with a custom drivetrain, you'll get more opportunity to really cater the drivetrain towards your design. And that's the only like real benefit to custom drivetrains. They're not going to offer much more speed. They're really just more to prove as a good base for your design. Kit-built drivetrains are very reliable. They're always going to work. However, some teams may be limited by them as they're very bulky, take up a lot of space, and they aren't built around your specific design. They're just built universally. So that's definitely something to consider when deciding on a drivetrain. You also have extension examples. I'm going to keep this pretty brief just because it doesn't really cater to this season specifically. However, you have vertical extensions, which reach a point that's higher on the field, and horizontal extensions, which can reduce driving by covering distance. And then outtakes, here are the 2 main examples. So like a bucket deposit that can dump game elements into the desired area, a claw deposit that is the same as a claw intake, however, it more accurately deposits elements. Another example of an outtake would be a shooting mechanism, specifically for this game, something that would shoot the game elements, the artifacts. The key to optimization. So, optimization in autonomous is mainly based around special sensors, such as cameras, odometry pods, as seen right here, and other sensors such as color, touch, and distance. These sensors can help your robot really give your robot a brain and a bunch of inputs to process and move based on. So for example, like the camera, you can track game elements and make your robot drive over to them. This is a special AI camera called the Limelight. It's more advanced, but this also has AI capabilities, so it's much better than this one. This is an odometry pod right here. You can use this to triangulate your position in the field in the autonomous period, making your programs much more reliable. And then to the left of the odometry pod, that's just a color sensor, and this can be used to sense the color of a game element. Optimization and driver controlled. So the use of automated programs can help really optimize driver controlled period. So like maybe a special program that can automatically pick up a piece and then transfer it. Also one that can maybe like suck in a piece and then get it ready to be shot out of a mechanism. Sensor inputs can be used to do this just like in autonomous, and also special mechanical optimizations can be used. So like for example, maybe like a small mechanical sweeper that could come from the bottom and push game elements away so it's more easily grabbable by the claw. So stuff like that. So yeah, thank you. This was my presentation.